Assalamu alaikum, my dear cadets of class 11. I welcome you all to my online physics class. During this ominous cloud of corona outbreak or pandemic corona, we are not able to stay at your home. That is second home. That's why our academic program is being hampered. And for these circumstances, our college authority has been taken some step, that is online effort, to solve this problem. That's why we are here. Okay. I think this online effort will be very helpful to all of you. Now, you know it very well that we are passing very tough and rough time during or due to this corona outbreak. That's why you are requested not to go outside of your home. And during this corona outbreak, please follow this instruction that is included in this figure. Before commencing my class, I would like to introduce myself. This is Kamruzzaman Khan, lecturer, Department of Physics, Borishal Cadet College. This class for cadets of class 11, subject physics, chapter 7 of first paper, and name of this chapter is structural properties of matter. I'm sorry for here. Okay, at first you should try your level best to observe this picture and what should be our today's topic. Guess it. Yes, our today's topics are chemical bonds, elasticity, stress, strain, moduli of elasticity, terminal velocity, and lastly viscosity. Learning outcome of my today's class: after finishing this class, cadets, you will be able to explain the nature of intermolecular force and explain the behavior of matter. And you will be able to explain different types of bonds of matter. You will be able to know Hooke's law, elastic constant, and Poisson's ratio. And lastly, you will be able to explain the flow of fluids, terminal velocity, and coefficient of viscosity. Now, the key points of my today's lecture: intermolecular force, bond and its types, elasticity, module, stress, strain, Hooke's law, viscosity, coefficient of viscosity, and terminal velocity. Let's have a closer look towards our today's discussion, that is about elasticity. Okay. At first, I will discuss about matter. Matter is anything that has mass and takes up space or place. All atoms composed of every tiny particles called atoms and molecules. Intermolecular force is referred to the force that exists among the molecules, and these molecules are attracted or repulsed for these types of force, and this is called intermolecular force. You know it very well that the range of intermolecular force is 10 to the power minus 10 meter. Intermolecular force in different materials. We know it very well that the intermolecular force in solid is very strong, and for this the particles or molecules of solid are very close to each other. And show this, see this picture, and here you are looking this. Now for intermolecular force for liquid, here the intermolecular force is relatively small. That's why the particles or molecules are not very close to each other. And lastly, intermolecular force for gases. Intermolecular force for gases, it is goes without saying that the intermolecular force for gases is not very strong, it is very low. That's why particles are able to move from each other very freely. Interatomic bonding, you know it very well from your class 10 that there are different types of bond, and for this bond atoms or molecules are attracted or bound together, and there are mainly two types of bond, that is primary bond and secondary bond. A bond that forms between atoms and that involves the sharing of electrons is called primary bond, and secondary bond, here there is no sharing or transfer of electron, and such a type of bond is called secondary bond. Okay, now I am discussing about primary bond. Yes, interatomic primary bond. Interatomic primary bonding may be of three different types. Ionic bonds. For ionic bonds, you know it very well, and it is happened between metal and non-metal, that is gas, result from the mutual interaction of positive and negative charges. The classic example is in sodium chloride. My dear boys, I don't want to discuss elaborately about bond, because you know it very well about bond, and it is elaborately discussed in your class, that is class 10. That's why I want to omit this section. So next is our covalent bond. Covalent bond is happened due to the sharing of electron. You know it very well. Class 11. Okay, I'm sorry for my interruption. Metallic bonds, you know it very well, these types of bonds will be happened between the atoms of metal, and this is a very strong bond. Okay, now I'm going to discuss about secondary bonds. So for secondary bonds, there are two types of bonds, that is van der Waals bonds and hydrogen bond. Okay, van der Waals bonds is very weak bonds. Firstly, hydrogen bonding. I will discuss hydrogen bond. Hydrogen bond between hydrogen atoms and atoms of the most electronegative elements, nitrogen, oxygen, fluorine, are called hydrogen bonds. Hydrogen bonds created with highly electronegative compound. When hydrogen is attached with highly electronegative compound, polarity is created at that time. My dear boys, you know it very well what is hydrogen bond. So I want to discuss about van der Waals bond, and it is not very important for you. That is, I want to say the bonding section or that I have been discussed till now from my beginning is not very important for you. That's why I am omitting this section. This is van der Waals bonds. Van der Waals bonds is happened between the inert gas, that is neon, helium, etc. Now I'm going to discuss about elasticity, and it is very much important for us. So I am drawing your attention, please, and I will ask you question from this section randomly. Okay, what is elasticity? At first, I want to discuss what is elasticity. That's why I'm okay, my dear boys. Let us suppose it is our spring, and there is no weight or force here. Now it is our second case, and this spring is suspended from a rigid position and it is now loaded somewhat force. Yes, after loading somewhat force, the length of this spring is being increased, and now we are withdrawing this force. That is, there is no load, and it is similar to our first case. It is our first case, it is second case, and it is third case. Okay, so you know it very well, or you are saying here that when you are withdrawing this applied force, the extension or this spring must have ability, or this spring is able to again its original shape or regain its original shape and size. That's why this spring is now similar to spring 1 and spring 3, but now step 2 or case 2 is not similar. Here is happened some elongation. That's why this is now extended, and this property is called elasticity. That is, when you are going to withdraw your applied force, then any body can regain its original shape and size, and this term is called elasticity. Now we can see the definition of this. Okay, the property of a body to regain its original shape or volume when the applied force is withdrawn is called elasticity, and the body, though so, elasticity is called elastic body. Now look at this figure, my dear boys. It's rubber. When force is applied, this rubber is extended, and when force is removed, this rubber regain its original shape and size. So it is called elastic body. Now plastic body, there are some types of body. When you are applying force on this body is not able to regain its original shape and size. Such a type of body is called plastic body. Okay, but my dear boys, you are seeing a figure, and it is not the figure of plastic body. Okay, it is the figure of elastic body. Yes, if it is plastic body, then there remains some error. That is, this body will never regain its original shape and size. Okay, after withdrawn its applied force. Elastic limit, my dear boys, elastic limit is a range. Within these range, an elastic body can exist its elasticity. When this body cross this limit, this body cannot show its elasticity, and this is the figure for elastic limit. Here, look at this picture. This is our equilibrium condition, and here this this body is elongated by somewhat force, by the application of somewhat force. And look at this point. If you increase your applied force, this body will never regain its original shape and size. That is, I want to say, this body will break. So that's why we are calling this is our elastic limit, and you know it very well that elastic limit is a range, and this is a range up to a elastic body can exist at elasticity. Okay, I think you can get this topic, what is elastic limit. Now I want to discuss elastic fatigue. Due to successive increase or decrease of stress, that is, you are suppose you are applying force continuously, and for this corresponding strain does not occur instantaneously. For this, strain does not occur instantaneously. That is, it will take some time. That is, it is feeling some tiredness. In this situation, a body slightly suffer from fatigue. That is, fatigue means tired. Okay. I want to say this body, when you are applying force successively or decreasing or increasing force successively, then this body will never want to show it elasticity. That is, it will take some time, and this term is called elastic fatigue. Okay. And rigid body, you know it very well. The rigid, what is rigid body? Rigid body, when you are applying force and applying force on a body and withdrawn this applied force on this body, from this body will never its original shape and size. Will never regain its original shape and size. Such a type of body is called rigid body. Okay, let's see the figure here. Yes, the structure is broken for some for the application of somewhat force, but the block are not displaced or deformed. Okay, so these are rigid body. Okay, before starting stress, I want to ask you some questions. Okay, my dear boys, am I audible?
Sir.
Okay.
Yes, sir.
Yes, sir.
Okay, Huzaifa, can you hear me?
Yes, sir.
Okay, Huzaifa, what is elasticity?
Uh, Elasticity, the condition of the object which is strength and from its equilibrium position to.
Okay. Okay, my dear boys, do you have or do you face, my dear boys, I want to say, do you have any questions or do you have any doubt about this discussion that I have finished till now?
No, sir.
Okay.
Sir, elasticity fatigue, sir. I didn't understand the
Okay,
elasticity fatigue.
Suppose you are applying force continuously. You are applying force continuously. That is, you are or you can decrease or increase this force on a body. At this time, this body will face somewhat tiredness. That is, this body does not want to show its elasticity. Okay, it will take some time to show its elasticity. Okay, can you get me?
Yes, sir.
Okay, that is called elastic fatigue. Okay.
Yes, sir.
Okay. My dear
Sir, I
boy.
have a question.
Yes.
Sir, is rigid body and plastic body the same?
No. Rigid body and plastic body will never same. Okay. Rigid body means if you are applied some huge amount of force, this body will never can regain its original shape and size when you are withdrawing your applied force. Okay. But plastic body, here is the difference. If you are if you are applying force on this body, and here can have some elongation or compression, but you are withdrawing your applied force. You are withdrawing your applied force. Then this body can regain its original shape and size, but it can cover somewhat. It can cover somewhat, but it can never regain its original shape and size. Can you get me?
Yes, sir.
Okay. I can.
Sir,
Yes.
a moment before you showed a picture where we saw the equilibrium, but what is the relationship here with the equilibrium, sir?
Equilibrium means initial condition. Equilibrium means initial condition. Okay. After applying somewhat force, elastic body must be elongated or compressed. Must be elongated or compressed. But when you have withdrawn this applied force or external force, then this body must have ability to regain its original shape and size. Okay.
Yes, sir.
Can you get me?
Yes, sir.
Okay.
Plastic body.
Do you have any question? Do you have any question, boys?
No, sir.
Okay. Can I continue my class?
Yes, sir.
Okay. Now I'm going to discuss stress. What is stress? Okay. Stress is the application of force per unit area. Stress is the application of force per unit area. Suppose this is our block and the area of this block is A, and you are applying a amount of force on this body, then this term is called stress. Okay, stress is similar to pressure. Stress is similar to pressure. Okay, and the next term is stress is equal to F by A, and its dimension is, you know it very well. How can we find out dimension? Dimension from this equation we can evaluate this dimension of stress. Now let's have a look. F is equal to ma, and this is our A, that is pi r square. A is replaced by pi r square. Now here is no A, pi r square. M, for M, the corresponding dimension of M is capital M, and A, for A is LT inverse 2. Okay, and for r square, pi is a mathematical operator or symbol. That's why it doesn't have dimension. But for r, we are getting dimension, and its dimension is L, and square is this term that is added here. Now, after calculating, we are getting this dimension, that is ML inverse 1 T inverse 2. Okay, you are frequently asked such a type of dimension, and it is coming as a question, MCQ question in your exam. So you should remember it. Okay, now our next term is types of stress. There are different types of stress, that is longitudinal stress, shearing stress, and volume stress. There are different types of stress. Longitudinal stress, it is related with length. Shearing stress, it is related with deformation, that is angle. And volume stress, it is related with the volume. Okay, what is strain? Strain is the amount for which a material has been deformed divided by its original size. Okay, let me clear what is strain. Suppose this is an object and its length is L. Its original length is L, capital L. Okay, and after applying somewhat force, it is elongated and its length has been changed. Now it becomes small l. This is our initial length and this is our changing length. So strain is defined by this way: L divided by capital L. Change of length divided by initial length. Strain is a ratio of same parameter, but its meaning is not same. L, small l for change of length and capital L for initial length, capital L for initial length, and it doesn't have unit. It doesn't have unit and dimension. It doesn't have unit and dimension. My dear boys, let me clear what is strain. Okay, this is our equation, that is del L divided by capital L. It is strain. Now look at this figure. What is the strain? This is our, okay, this is our object that is having length capital L. After applied somewhat force, this object has been compressed and its length is small l, and this amount of length has been changed. So this is del L. This is del L. My dear boys, I have drawn your attention, or I'm drawing your attention, please. You have to remember that what amount of length change here, what amount of length change here. Yes, this is our changing length, that is defined by del L, that is
Stress. The second one, sir.
yes.
Will you explain?
Obviously, I will explain. Okay, but I don't explain till now sharing stress. Okay, but now
Okay.
I am explaining only stress and strain. You have to know what is stress and strain. Okay, after getting this stress and strain, we will discuss about volume stress or volume strain, sharing stress or sharing strain. Okay.
Okay, sir.
But you have to remember here, strain is del L, that is change of length. How amount of change of length you are getting, okay? But you can never use this amount of length, okay? Or you can never use this amount of length after the application of force. Okay, you have to use only the amount of change that you are getting. Okay, boys, can you hear me?
Yes, sir.
Okay, now can I omit this stress and strain term? Is it clear to all of you? Boys, is it clear to all of you?
Yes, sir.
Yes, sir.
Okay. Now Boys, I'm hearing all of you, okay? So be careful. I'm hearing all of you, so be careful. Now I'm going to discuss about types of strain. There are three types of strain: longitudinal strain, that is related with length. Okay. Okay. This is related with length. And shearing strain. Okay. A little bit ago, someone of you have asked me what is shearing strain. Am I right? Boys? Hello?
Yes, sir.
Okay, a little bit ago, some of you have asked me about shearing strain. What is shearing strain? Am I right?
Yes, sir.
Okay, I'm going to discuss about shearing strain. This is our block. Okay, let us suppose it is our block and the length of this block is BC. Okay, and this is the width of this block. That is, you may, it is defined by letter D, that is CD. Let us suppose you are applying somewhat force. Let us suppose you are applying somewhat force, and after the application of force, this is deforming. Now, this B point is replaced by B prime. This B point is replaced by B prime. Now this is the shape and size of our block. This is the shape and size of our block. Okay. Here you are getting somewhat displacement. You are getting somewhat displacement because it is our initial position and this is now our final position, and this is B prime. Am I right? This displacement is B prime. That is called relative displacement B prime, and the intervening distance, that is BC, because this is our length BC. So you know it very well that strain is ratio of same parameters. So this is B prime is also length and BC is also length. Okay, and this is called shearing strain. This shearing strain you can only get from deformation. This shearing strain you can only get for, my dear boys, don't, my dear boys, don't play with me. My dear boys, it's my earnest request to all of you, don't play with me, okay? I have ability to notice you who is or who are doing such a type of devil work. Can you hear me?
Yes, sir.
Sure.
Look at this figure. After application of force, deformation is occurred here. After the application of force, deformation is occurred here, and this is the similar case of shearing strain. This is the similar case of shearing strain. Okay.
Yes, sir.
Okay. Can I change it? Can I change it?
Sir, in this
Okay, sir.
case, both of them are sharing strain, sir.
Yes.
Are they?
This is the identical figure of that case. Okay. This is the identical figure. Identical figure. Okay. This is the identical figure of that case. Look at this. This line and this line is it same? Obviously. boys? Let's have a video on stress and strain.
Okay, say we apply a downward force F on the surface area of a beam. Here, the force is trying to compress the beam from the top. Due to this, the beam will experience some stress. It is just an uncomfortable state experienced by the object, which is the beam in this case. The atoms inside are little too close than they want to be. This results in interatomic and intermolecular forces, and if the applied force F is within the elastic limits of the material, these forces bring back the object to its initial state when the applied force is removed. Mathematically, stress is defined as force per unit cross-sectional area. So it is F over A, where A is this cross-sectional area. What if I increase the force from F Newton to say F plus 10 Newton on this area A? Intuitively, we know that if we push it with a greater force from above, then the beam will experience more stress. Mathematically, this new stress will be F plus 10 over A. The numerator increased and the denominator remained the same. It means that this ratio is greater than this one. So if we increase the force, the stress will also increase. Next, what will happen if I increase the surface area from A meter squared to say A plus 10 meter squared? Will the stress increase in this case too? The stress will decrease in this case because the denominator increases with the numerator remaining constant. Now, what is the SI unit of stress? Any guesses? Stress is force per unit area. The SI unit of force is Newton, denoted by N, and that of area is meter squared. So the SI unit of stress is Newton per meter squared. However, this unit is given a name and it's called Pascal, denoted by PA. Now we know the basics about stress. What is strain? In very simple language, one can define it as change in dimensions per unit of original dimensions. When any object is under stress, it will change one or more of its dimensions. The amount by which the object's dimensions will change will depend on the force applied and the materials the object is made up of. In our example, L is the length of the beam and it's experiencing some force. Hence, it will deform and its length will change by, say, delta L. Strain is defined as change in length per unit of the original length. Mathematically, it is delta L over L. So what does this ratio do? Well, the ratio compares the change in length that resulted due to force with the original length of the beam. Here, strain is calculated in terms of length of the object. But the length may not be the only quantity changing due to deformation. We can also find the strain in terms of area and volume. Let's take an example of a sponge ball of volume V. When it's compressed, its volume decreases. So the strain in terms of volume is delta V over V. Note that delta V is the change in volume and not the volume of the deformed sphere. Let's take another example where a thin rubber sheet is stretched equally from the opposite sides with a force F. And that will result in a change in the area. So the strain experienced by the rubber sheet is delta A over A. Delta A is the change in area of the sheet and A is the original area of the sheet.
Okay, my dear boys, after observing this video, I think you are getting clear concept about stress and strain and its different types. Okay, let's see this curve here. Strain is plotted along x-axis and stress is plotted along y-axis, and this is the figure. This is the initial position of this spring, and this is the elongation, and this is also the elongation, and this elongation is much more than that of this. Now we are going to discuss about this. Here, when you are applying load on this spring up to a limit can show its proportional relation. That is, if you are increasing load, your extension or its length will be increased. And from this A point, that is OA, indicates the proportional limit. And when the load, amount of load is increases and it is crossing point A and reach at point B, then from A to B, from A to B, I am repeating it, from A to B there is no proportional relation. That is, if you are increasing load, elongation is not increasing or will not increase, okay, with this application of force. Now if you are increasing this force more or load more, then the spring, elongation of this spring will cross this point B and reach at point C, and from BC is called the existence of plasticity. If you are increasing your application of load, then this length or then this spring will reach at point B, and it is called breaking stress. What is breaking stress? I will define it a little bit later. And now I am saying, if you are increasing the amount of force, then this elastic body will break. Okay. So this is our last limit of application of force. Okay. If you cross this limit, this body will never can regain its original shape and size. Breaking weight and breaking stress. The minimum applied force or load for which a substance either breaks or snaps is called breaking weight or breaking load. Breaking stress, the force per unit area for which the body breaks is called breaking stress, and it is defined by breaking weight divided by area. Now this is math related breaking stress. Okay, this is the equation of breaking stress, and this is the equation of breaking weight. You know it very well. Weight is mg, and this m is replaced here as breaking mass, and this is the multiplication of acceleration due to gravity. Okay, after putting value in this equation, you can get the amount of breaking stress and breaking weight. Now I'm going to discuss about Hooke's law. What is Hooke's law? Scientist Hooke said, within elastic limit, stress is proportional to strain. Now this is our equation. Stress is proportional to strain. From this equation we can get stress is equal to constant into strain, and now we can write constant is equal to stress by strain, and this constant is called coefficient of elasticity. This constant is called, I am repeating, this constant is called coefficient of elasticity or modulus of elasticity, and it is defined by a letter that is Y. That is capital Y. Okay. Its another name is Young modulus. Its another name is Young modulus. Okay. Now look at this figure here. The amount of, this is the zero position, the amount of force is increased, then the elongation is increased, and for this elongation this spring is storing resistance, and it is called restoring force. I want to discuss about restoring force. What is restoring force? Look at this. Suppose this is rigid position, and from this rigid position, this spring is placed here, and now it is elongated, or this spring is elongated somewhat force, or you are stress this spring with somewhat load. Now you are withdrawn this force, it is getting back its initial shape and size. It is our figure 2, and this is our figure 1. This is initial position. There is no load, but in figure 2 there is application of load, somewhat load. For the application of somewhat load, this spring is elongated. After withdrawn this application of load, this spring can regain its original shape and size, but your force direction, that is the force is applied here, its direction is like that, and due to the application of your force here is developing somewhat force, that direction is vice versa of your applied force. This is reverse, and this force, this spring can regain its original shape and size. That is number 3. And this force is called restoring force. The reciprocal force of your applied force, is called restoring force. I am repeating, is called restoring force. Okay, this force direction is opposite to your applied force or to your load. Okay, now modulus of elasticity. Within this limit, the ratio of stress and strain is called constant. You know it very well from the Hooke's law. This constant is called modulus of elasticity, and its another name is Young modulus, that is defined by y. Y is equal to stress divided by strain. Stress is equal to F by A, and strain is equal to small l divided by capital L, small l divided by capital L. Here small l means change of length. Here small l means change of length, that is similar to delta L. Okay, you can use small l or delta L. The unit and dimension is Newton per meter square or Pascal, and dimension is like that. So this is our dimension, and this is our unit, and Newton per meter square is equivalent to Pascal. So you can use Pascal or Newton per meter square. Okay, there are 3 types of modulus: Young modulus, modulus of rigidity, and volume or Mach modulus. Okay, let me define what is Hooke's law.
The Hooke's law. Robert Hooke, an English physicist, stated that the empirical law in 1660, which is today known by the name Hooke's law. What does empirical mean? It means the law was derived using observations. It states, for elastic deformation in a string, the deforming force is directly proportional to change in length. Consider a spring of length L whose one end is fixed from the end. Suppose the stretching force F is applied on the other end. Now let the change in its length be delta L. The law states that the force F is directly proportional to delta L. Now what do we mean in mathematics when one quantity is directly proportional to the other? It means that one thing is some constant times the other. So we can write force F is K times delta L, where K is the proportionality constant. This is the mathematical form of Hooke's law. In some textbooks, you must have noticed the presence of negative sign on the right side of this equation. The negative sign comes due to the slightly different version of the Hooke's law being followed. We can also define Hooke's law as
Actually, sir, nothing is audible, sir. We cannot hear you.
Sir, we can't hear you, sir.
Sir, we can't hear you.
Now, am I audible?
Yes, sir. No.
Yes, sir.
Yes.
Yes, sir.
Okay, my dear boys, let me finish this. There are three types of modulus. There are three types of modulus. Okay, I will finish it within 2 minutes. Let us suppose it is modulus, young modulus. Young modulus is equal to stress that is longitudinal. It is related with length. It is related with length. Stress F by A and strain L divided by capital L. Okay. And now the next term is Bach modulus. Bach modulus for this is volume modulus. Okay, this is related for volume. This is related for volume, and it is defined by B or it is defined by B or K, B or K, and it is also F by A divided by capital V or small v. Capital V for initial volume, small v for change of volume. Okay. And next term, sharing modulus of rigidity. It is also called for modulus of sharing. Okay. Here you are applied force that is F, and it is defined by eta. It is defined by eta. You know every modulus of elasticity is defined by stress and strain. Okay, stress and strain. Strain, you should try to recall, that is a little bit ago we have discussed B prime divided by BC. This is our sharing strain, and this sharing strain is defined by a theta. This sharing strain defined by a theta, so we can write here theta. Theta is sharing strain. That's why eta is equal to stress divided by strain. This is our modulus of rigidity. This is our modulus of rigidity. Okay, my dear boys, is it clear? Hello. Boys,
Yes, sir.
okay. Work done due to strain or stored potential energy. Let us suppose you you are taking an object, that is our spring, and the length of this spring is capital L, and due to the application of some more force, the length of this spring is being changed, and let us suppose it is small l. Okay, so due to this change we are getting somewhat work. This work is the dw is equal to, this work is, you know it very well, work is equal to f work is equal to fx. You know it very well, work is equal to fx, work is equal to fx. And now this is work for small change of length. That's why we can write fdl because this length is taken here as small l. So this x is replaced by dl and f is f. So we are getting dw is equal to fdl. This is our small amount of work. Okay, and you know it very well about differentiation. From differentiation we can get the total amount of work done. For integration, from integration we can get the total amount of work. Okay, now I am trying my level best to do it or complete it. This is the symbol of integration. You are looking here, and we have started here from 0, and we are getting change of length is small l. Okay, we are getting change of length is small l. So the integration of dw is equal to integration of fdl, because dw is equal to fdl, and it is also start from 0 to l. But I have a little mistake. I have a little mistake here, because you can never write small l here. So this is the relation with w. So we are getting total amount of work from 0 to w. Okay, from 0 to w. That's why I have done a mistake here, and from this mistake I think you are getting clear concept about this work done. We are getting total amount of work from 0 to W. That's why I have written here 0. This is lower limit, and this is higher limit W, and here this is 0, this is L, because D is related with small l. Here D is related with small l, and here D is related with W. That's why 0 to W and 0 to L. Okay, now let's see this calculation. We know it very well from the Young modulus y is equal to FL divided by AL, and from this equation we are getting F is equal to this amount of force, and after putting the value of F here, we are getting this equation. Now after integration we are getting integration. Yes, you have to know what is integration. Yes, we are doing integration L and DL, 0 to L. Okay. And now 0 to L, for 0 to L, you know a equation. This is general equation for integration x to the power n dx is equal to x to the power n plus 1 divided by n plus 1, and we are putting this equation here. Now we are getting, look at this figure and look at this writing. Yes, there is power of L is 1. Okay. Now I am applying this equation here. L 1 plus 1, that is n plus 1 divided by 1 plus 1, that is n plus 1. Okay. Boys, try to understand this. Okay. Now you are getting L square divided by 2, and this is our equation, L square divided by 2. And this is the amount of work done due to strain. This is the amount of work done due to strain. Okay. And stored potential energy per unit volume, that is, this amount of work is divided by volume. Volume is equal to AL. Boys, volume is equal to AL. This amount of work is divided by volume, because we are dividing this for getting energy per unit volume. For getting energy per unit volume, that's why this V is written here. This V is written here. Okay. And after calculating, we are getting like this, half YL by L. This is similar to stress, and small l by capital L, this is strain. That's why you can write the stored energy or storage energy per unit volume is half into stress into strain, half into stress into strain, half into stress into strain. This is our most important equation. This is also our most important equation. You have to remember, this is the amount of energy per unit volume, and this is the amount of energy or work done due to strain. Okay. It is not related with the volume. It is not related with the volume, but it is related with the volume. It is related with the volume. My dear boys, hello, hello,
Yes,
can you hear
yes
me?
sir.
Yes, sir.
Yes, sir.
Boys, please tell me from the very core of your heart, can I continue this class or it is enough for today?
Sir, it is enough for, I think.
It is enough for today. Okay,
Yes, sir.
boys, is it right?
Yes, sir.
Yes, sir.
Now I'm going to finish this class. Okay.
Okay, sir.
Okay, my dear boys, at a glance, what I have discussed today: chemical bond, elasticity, stress, strain, and moduli of elasticity. Now, if you have any questions or query, please ask me through your message, or you can write it in box, and I will try my level best to solve this types of questions, some sorts of questions, that is knowledge based questions and understanding level or comprehension based questions are inserted here. Look at this very deeply. Types of questions, that is application level questions and higher order level questions are inserted here. You should try to solve these questions. Okay. sample of MCQ. Some sorts of MCQ are included here. You can solve these questions, and if you face any problem, please tell me. I will try my level best to solve your problem. Let's see the home task. Solve these CQ questions. After solving, you can send me to our website and make 20 MCQ. Make 20 MCQ on the basis of my today's discussion, and it is very important part to you. Every Thursday online exam will be open, so you should try level best to attend here. Follow this instruction for corona. You know it very well that we are passing very tough situation or time. Thank you very much for attending my online class. I hope you must try to your level best to follow the instructions that I have been given here. You know it very clearly that we are passing very tough time due to COVID-19. During this corona outbreak, going outside of home is very risky of us. So never ever make any plan to go outside of your home. Spend time with your family and your parents. Never neglect your regular study. You should be very punctual about your online class. You should be very punctual about your online class.